I think all of us have a sort of intuitive notion of what it means to factor a polynomial. And now we're going to make this precise with the following definition. So let's let D be an integral domain. And now we're going to define what's called irreducible versus reducible. And so a non-zero f of x in D bracket x that is not a unit is irreducible over D. If whenever f of x can be factored as g of x times h of x, either g of x is a unit or h of x is a unit. There's a little bit more. There's another sentence I'm going to add to this definition, but let me just kind of slow down and talk about this for a minute. So what we're defining is irreducibility, and you want to think of that as sort of impossible to factor, right? You can't factor it in any interesting way. And so that's the idea. A polynomial is going to be considered irreducible over the ring of coefficients that you're working in if any time you factor your polynomial, you've done it in a non-interesting way. All you've done is pull a unit out. Right? So if that's the only way you can factor it is in this sort of trivial way where one of the two factors is a unit, then we say that the polynomial is irreducible over D. And so then to finish off this definition, we say otherwise f of x is reducible over D. Now notice I've underlined not just the word irreducible and reducible, I've underlined the over D part. And that's actually important because what we'll see is it's possible, depending on who your ring of coefficients is, the same polynomial may be reducible in some settings and irreducible in other settings. Okay, and so let's immediately look at an example here. So let's consider the polynomial 2x squared plus 4. Now, depending on where I view this polynomial, right, sometimes it will be reducible and sometimes irreducible. I can factor this polynomial, of course, as 2 times x squared plus 4. And note that if I look at this polynomial and say, hey, we're using integers as coefficients. Well, in z bracket x, that's not a unit, and neither is that. And so we have factored this polynomial in a non-trivial way in z bracket x. So this polynomial is reducible over z. So this one is reducible over z, and the reason is that 2 and x squared plus 4 are not units in z bracket x. However, right, I mean, so now I'm going to say, well, okay, fine, these coefficients, they're integers, but they're also rational numbers. If we view 2 and 4 as rational numbers, and then these polynomials as living in q bracket x, well, 2 is a unit of q bracket x, right? Its inverse is the polynomial 1/2. And so this is a trivial factorization when it comes to viewing this in q bracket x. So this is irreducible over q. All you did was pull a 2 out. That's easy, and it's a unit, right? We don't care about pulling units out. You can always pull units out, and that's not an interesting way of factoring in the polynomial. It's also, so this is also irreducible over r for the same reason, right? 2 is a unit of r bracket x. So the reason here is 2 is a unit in Q, and I'll just put Q comma R. So for the same reason, this polynomial 2x squared plus 4 is reducible. Is irreducible. And notice, this is just one of many ways to pull a unit out of this polynomial. So for example, it's also equal to 4 times 1/2 x plus 1, 1/2 x squared plus 1. In fact, there's an infinite number of ways to pull units of r or q out of this polynomial, right? It's also equal to pi, let's do 2 pi, 2 pi times, so now this would be 1 over pi x squared plus 2 over pi, right, factored in r. Right? So there's an infinite number of ways to pull out units. That doesn't give you any information about the roots of the polynomial. We don't care. If you can pull units out, so what? Right? That is not an interesting way to factor the polynomial. And then, okay, so, we could also view 2 and 4 as complex numbers. So we could view this polynomial in C bracket x. And then, of course, we can factor it. So this would be what? So this is 2 times x minus, God, sorry, everyone probably saw that typo there. 2, oh man, did I screw this all up? One. Yeah, and then this should be what, 2 over pi. Did I get this right? 2x plus 4, 2, 4. Yeah, sorry. X minus I root 2 times x plus I root 2, which would be in final form, let me put this as 2 separate polynomials, 2 2x minus 2I root 2 times x plus I root 2. So this is reducible over C, and the reason neither of these polynomials are units in C bracket x. So neither is a unit in C bracket x. See, these kind of little arithmetic mistakes, that's why I need you in this class right now. Right? Normally when I'm in front of the board and I make a trivial arithmetic mistake, 4 hands go up and stop me before I go too far. Okay, so let's look at some more examples. Next example, so let's see, let's look at x squared minus 5. This is irreducible over q, right? We can see, we know how to factor this polynomial, right? This is x minus root 5, x plus root 5, right? That's reducible over q. So this is, over r. It is reducible. So hopefully it's making sense why we have the term irreducible over D, right? Reducible over D. It depends on, when you have a polynomial, depending on where you're viewing these coefficients, right? It's going to make a difference. So let's look at one more example. X squared plus 1 is irreducible over Z3. But it's equal to x plus 2 times x plus 3 if we are working in Z5 bracket x. And so is reducible over Z5. You might ask the question, how do you know that it is irreducible over Z3, right? I mean, I produced the factorization to show that it's reducible over Z5. How do I know that's irreducible over Z3? Well, think about the factor theorem. If we took this polynomial and we were going to factor it, then it would have to be in a degree 1 times a degree 1, which would then tell us exactly who the roots are, right? And so if we could factor it over Z3 bracket x, or in Z3 bracket x, we would get something of the form, x minus a times x minus b, and that would tell us that both a and b are zeros of the polynomial. And so if I take the elements from Z3, okay, so who would they be? If I plug a 0 in, I don't get 0. If I plug a 1 in, I don't get 0. If I plug 2 in, I don't get 0. And so there's an argument for why this polynomial is irreducible over Z3. It's because it has no zeros in Z3. The definition of irreducibility and reducibility, it's a little bit clunky. It doesn't really, doesn't really roll off the tongue that nicely. Now, here's what's nice. Okay, so let me write this observation. We'll be able to sort of simplify the definition if we're working where in a situation where the coefficients come from a field rather than just an integral domain. And so here's the observation. The units of f bracket x, where f is a field, are the non-zero elements of f. So the elements of f star. And so this allows us, right, so let's say it like this, thus, or this allows this, how do I word that? So this allows for a more convenient characterization of reducibility, or of, let's say, irreducibility. Over a field F. And so it'll go like this. So a non-constant polynomial non-constant polynomial, say f of x in capital F bracket x is irreducible over f if f of x cannot be expressed as little f of x equals g of x times h of x, where both g of x and h of x are polynomials in f bracket x whose degrees are strictly smaller. So where the degree of g of x and the degree of h of x are strictly less than the degree of f of x, right? So that means then that a polynomial is reducible over f. And this is not a definition, but let me just underline it here. So a polynomial then is reducible over f if it can be expressed as the product of two polynomials of lesser degree. All right, so that's a nice quick way to describe reducibility over a field. Now, deciding whether a polynomial is reducible or irreducible over a given field even, that's a tough job, right? I mean, this is where this will eventually lead us to Galois theory. So in general, deciding whether a polynomial is irreducible over a field F is difficult. So what we're going to do is develop various tests that allow us to decide in certain cases that whether a polynomial is reducible or irreducible. And so the first one goes like this. So this is theorem 23.6. And this, we'll refer to this as the degree 2 or 3 test. So let's take a polynomial. So let's let little f of x be in f bracket x, where the degree of f is either 2 or 3. So where the degree of f of x is equal to 2 or 3. Then f of x is is reducible over f if and only if there exists some, say, alpha in f such that f of alpha is equal to 0. This is what I was alluding to a minute ago when I was working over or looking at x squared plus 1 and working over z3. Right? So what this says is if you have a polynomial of degree 2 or 3, then you can factor it. It is reducible over f if and only if there's a root living in f. Right? So if and only if there's a 0. Now this only works for degree 2 or 3. So in the forward direction, so let's assume f of x is equal to g of x times h of x, where g of x and h of x in f bracket x have lesser degree. Well, what does that tell us then? It tells us that at least one of either g of x or h of x is a 0, right? So, yeah, let's just assume that the first one. So we can then assume, I think I just said 0, but I meant 1. Then we can then assume, without loss of generality, that. So let's see, if we factor f of x, and f of x has degree 2 or 3, in this way, then at least one of these polynomials has to have degree 1. If if the degree is 2, then both of them have degree 1. If the degree is 3, then one of them has degree 1 and the other has degree 2. So we can assume without loss of generality that the degree of g of x is equal to 1. And so g of x can be expressed as ax plus b for some a and b in f, where A is not equal to 0. All right, this has to have degree 1, which means A, that coefficient can't be 0. So now, let's see. So from this, we should be able to identify a 0. So letting alpha equal, so let's see, who's the 0 of G going to be? It's going to be negative alpha inverse times, or A inverse times B. So letting alpha equal negative A inverse B, we have F of alpha equals G of alpha times H of alpha, which equals 0 times H of alpha, which equals 0. Okay, so now for the reverse direction. So if alpha in F is a 0 of f of x, then by our previous theorem, so this was this is the factor theorem. I don't remember what the number is, but so then if that's what, so then f of x is equal to x minus alpha times say h of x for some h of x in where am I? F bracket x. That, sorry, I'm running out of room here, but that's the factor here. Okay, so that completes the proof. Let's see how to make use of this. Yeah, this result, so let's say it like this. This result, and we'll see this more and more, this result is especially useful over ZP. And we will definitely make use of this fact over ZP. So let's see. So let's say determine whether the following polynomial f of x equal to x cubed plus x squared plus x plus 1, x squared plus x plus 1 is irreducible over Z5. According to our previous theorem, all I need to do is take the elements of Z5, plug them into the polynomial. If we get 0, the answer is yes, it's reducible. If the answer, well, I guess I should say no, it's reducible. And if we get non-zero, then we say it's irreducible. So you can check f of 0, that's equal to 1. F of 1 equals 1, 2, 3, 4. F of 2 what's that equal to? 8 plus 4 plus 2 plus 1, 12, 14, 15, right? 12, 14, 15, which is equal to 0 in Z5. And so what's the answer? It is not irreducible, or we can say so by theorem 23.6, f of x is reducible over Z5. Remember that this only works in degree 2 or degree 3. right? This is going to become important to make that distinction. So when you have a polynomial that's degree 2 or degree 3, all you need to do is run through all the zeros if plugging in all those elements. And notice, if you got a finite field, then there's only a finite amount of work to do. Plug in those elements, and the answer is either yes or no. It can become more difficult if you're working over an infinite field, because then you, of course, don't have the time to plug in all infinite number of elements of the field. Let's see what time we got here. Yeah, I think that's enough for now. So we're going to start some fairly heavy-duty work, right, that'll lead to a few new tests. But we'll pick up with that next time, okay?